Now ready to define what it means for an LTS M to satisfy a formula phi in one of its states S. It simply means that all paths of M that start in S satisfy phi with respect to the labeling of M. Remember that we already know what it means for an infinite sequence, in particular for a path, to satisfy an LTL formula with respect to a given labeling. What we are doing now is extend this definition to entire LTSs. So, for an LTS M and one of its states S, and for a formula phi, we define this relation, written M, S satisfies phi, and read M satisfies phi in state S, or phi holds for M in state S, to mean that for every path pi of M, starting at state S, pi satisfies phi with respect to the labeling L. Okay, let's consider some examples. Here is our small LTS from before, and also it's unwinding into a tree for those who prefer chasing the paths there. Does our LTS satisfy in state S0 the formula P and Q? Written again, M, S0 satisfies P and Q, and read M in state 0 satisfies P and Q. Yes, it does. All paths that start in S0 obviously satisfy both P and Q, simply because the atoms P and Q are true at S0, given that they label S0. It also satisfies in state S0 the formula not R, because the atom R is not true at state S0. Remember that we label each state with all the atoms that are true at that state. So if an atom doesn't show up in the labeling, it means that it is not true, in other words, false at that state. It also satisfies in state S0 the formula next R. This is because all paths starting in S0, so they can go either this way or this way, will have R labeling their second state. That is the next state after the initial one. So all paths will satisfy next R. Essentially because both S1 and S2, which are all the possible second states of paths starting in S0, do have R as a labeling. On the other hand, our LTS does not satisfy in state S0 the formula next Q and R. This is because there exists a path, the one going through S2, which at the second position does not have both Q and R holding, but only R. So this particular path does not satisfy next Q and R, which means that our entire LTS does not satisfy next Q and R. Notice something important. To argue that an LTS satisfies a formula in a given state, we must argue that all paths starting in that state satisfy that formula. On the other hand, to argue that an LTS does not satisfy a formula, as we did last, it suffices to find one path that starts in that state and does not satisfy the formula. More examples. In S0, our LTS satisfies always not P and Q. To see this, note that whatever path we take, we never get into a state where both P and Q hold, simply because there is no such state. So, trivially, always not P and Q holds. Now, always R holds in state S2. So it is important to indicate at which state we want our formula to hold. In this case, we consider the state S2. Why does always R hold in state S2? Because any path starting in S2 keeps repeating S2. So cannot go anywhere else. And R is true and stays true. In S0, our LTS satisfies eventually not Q and R. so it satisfies eventually not Q and R implies always eventually R. Why is that? Well, let's consider a path that starts in S0. We need to show that it satisfies a formula of the form something implies something else, namely eventually not Q and R implies eventually always R. By the semantics of implies, what we need to do is assume that our path satisfies eventually not Q and R, and we must prove that it also satisfies eventually always R. So let's consider such a path, starting in S0 and satisfying eventually not Q and R. We can see that this path must reach a state that satisfies not Q and R, right? By the semantics of eventually. That is, it must reach a state that satisfies R but does not satisfy Q. Since the only such state is S2, so all the other states either satisfy Q or satisfy not R. So the only such state where not Q and R hold is S2. So this means that our path must visit S2. But once visiting S2, there is no way out. It will stay in S2, which means that eventually, namely at the time when it enters S2, always R will hold, since R holds in S2. We have just shown that such a path will satisfy eventually always R. Okay, so we started with a path about which we assume that it satisfies eventually not Q and R, and we show that that path must also satisfies eventually always R. So the implication is proved. Here are some other examples, through which I'll go a bit more quickly. In S0, our LTS does not satisfy always eventually P. A path failing to satisfy this is the one that visits S2. So this path visits S2, and there P does not hold. In S0, our LTS satisfies always eventually P implies always eventually R. Remember that always eventually something means that something holds infinitely often. Now, the only path starting from S0 where P holds infinitely often is the one that avoids S2. So it has to go like this. Otherwise, P would not hold infinitely often. But that path also has R holding infinitely often. So every other time, R also holds. So our implication is proved. On the other hand, the converse is not true. In S0, it is not the case that always eventually R implies always eventually P. For example, a path that visits S2 and necessarily stays in S2 will have R but not P holding infinitely often. So we have our counterexample. Here is a homework exercise that will allow you to practice LTSs and their satisfaction relation. You are given an LTS as a picture and are asked to write its components in mathematical notation, then to draw its unwinding tree, then to describe its paths, and then to determine the truth of some formulas in some states. Note that points 1, 2, and 3 will help with points 4 and 5. Another homework exercise asks you to express some properties as LTL formulas for our process and critical section LTS, and to check whether they hold. These properties are a safety property, saying that only one process may execute a critical section code at any point. A liveness property, meaning that whenever a process requests to enter its critical section, it will eventually be allowed to do so. And a non-blocking property, stating that a process can always request to enter its critical section. So please give some thought on whether you can express these properties in LTL, and if you can express them, ask yourself whether they are true for our example LTS with a processes and critical sections.